Okay. Okay. All right, let's jump right into it. 5 more Leetcode problems, starting with number 116. Start the timer. 116. Populating next right pointers in each node. You are given a perfect binary tree where all leaves are on the same level and every parent has 2 children. The binary tree has the following definition. Struct node, it's got a value, which is an integer, a left node, a right node, and a next node. Populate each next pointer to point to its next right node. If there is no next right node, the next pointer should be set to null. Initially, all pointers are set to null. Okay. So the image really explains it because I had no idea what it was saying before. It doesn't say what a perfect binary tree is, but I assume that means where all leaves are on the... Oh, okay. It's like fully filled binary tree. Yeah. Okay, given the root of a perfect binary tree, populate each next pointer to point to its next right node. Okay, so a few ways to do this. One kind of way that is kind of cheating would be to reuse our solution to a previous problem that gives the level order of the binary tree as the step 1. So generate the level order. Step 2, go through the level order and get the nodes to point to the right place. That would work. It would be like on space, on space, on time. I think there's a way to do this with O1 space, so to only have a constant amount of, or maybe not O1 space, but better than having generating a full copy of the tree and then iterating over the copy a second time. So could we do this while we're in the middle of a traversal? We'd have to remember... we would kind of want to traverse backwards. So start from the right side, go to the left side, and at each level, remember the last node we saw so that the next time we get to that level, we can point this node to that node. Yeah, that's what we would want. So I think if we did a backwards pre-ordered traversal, we would get what we want. So basically, def traverse takes a node, usually they don't use the string version of the type. I wonder if there's a reason why the type's not available here. Okay, so you start, let's not call this root because that's going to be confusing. We need a data structure on the outside that remembers the write node at each level. Write nodes by level. Let's say that's a list. And it's like a list of node, of node or none. Traverse is also node or none. So, we're going to be traversing in a backwards pre-order fashion. So basically, traverse node.right, traverse node.left, and then deal with node itself. Node.right. You know what? Actually, we need to deal with node in between here. We need to or first, because it's a pre-order, but it's backwards. Backwards just means you swap left and right. Pre-order still means that you deal with node first. Okay, so what does dealing with node mean? It means it means two things. So you set its next. That's what they called it, right? Yeah. Node.next equals write nodes by level. And you get the depth. So we're also going to need the depth here. Depth is an integer. When we start, we're going to call traverse with the root and a depth of 0. And then what do we return? Do we return the root again at the end? Return root. Okay. So grab the right node at this level. So right node by level depth. Then now put myself as the new right node at that level. So equals node. And then traverse right and then traverse left. And keep track of depth. So whenever you're going down, depth goes +1. The last thing is I just need to make sure that I'm handling when I'm handling the nulls at the end, so that, which is the first things that you run into. It's when the list doesn't have the right length yet. So if depth is greater or equal to the length of the list, then we have to expand the length of the list so that we're going to be able to add our node to it. So dot append none. Starts as none. And then it gets replaced right away here. And then only if we didn't have to do that, do we know that there's going to be a value at depth. So let's give that a go. We also need this base case of the traversal, if not node return. Nothing to do. Okay, let's submit that. Okay, one down. Yeah, it's interesting that we're on the right side of this curve here because we used log n working space plus the space of the output, which is on, but sometimes you distinguish between the amount of space your code needed and exclude the space that the output required when you're talking about working space. So that's pretty good. Log n space on time. I wonder if people had better solutions. People are doing it in O1 space. How would you do that? Oh. Well, this is hard to read, but I was just thinking, I guess if you were traversing the tree in the right order, well, I was gonna say if you traversed it in the right order, you could only have to remember one node at a time, but I'm not sure how you could do that actually. I'm not sure that. Let's see if we can find someone with a good explanation of how it's O1. Okay, this person is really not using any extra space. And how are they doing it? Yeah, this is what I was thinking, is if you're doing a recursive traversal, you're using log n space anyway, because you have to store the recursive stack as you know, in memory. You don't have to write, you don't write that part in Python, but that's what Python is doing. So I guess this is the idea of what they're doing with the recursive call, and then they unroll the recursion into this harder to read version. Connect nodes children. So this makes sense for whenever you have two children, you connect the left one to the right one. What about the right one to the next right, to the next left one? If node.next, yeah, it's lots of different answers. I think this is closer to what we're doing. That's not quite what we're doing. Okay, so I'm just trying to understand this answer before I move on. So Fn is some kind of tree traversal. You start at the root. At each node, you connect its left to its right. Oh, then they take advantage of the fact that the... Okay, that's interesting. They take advantage of the fact that they already... Okay. So from 2, the two things you do are you connect 4 to 5. So you connect your left dot next to your right. And then you connect 5 to 6. And the way you do that is you follow the next link that you've already made for yourself and go left. That's how you get 6. And 5 is just yourself dot right. So I'm doing a normal tree traversal. I'm not taking advantage of the fact that I've got these new links that I can traverse. Interesting. Okay, next problem. Start the timer. Reset. Start stopwatch. 117. Populating next right pointers in each node 2. Given a binary tree node which has an integer value, a left node, a right node, and a next node. Populate each next pointer to point to its next right node. If there is no next right node, the next pointer should be set to null. Initially, all pointers are set to null. This is the exact same problem as last time, except we have no... except we don't have a guarantee that the binary tree is full. So that trick of traversing the nodes wouldn't work, but that also means that the solution that I had to the last problem is actually probably the best solution to this problem. Let's immediately submit that. There we go. Under a minute. We just spent a bunch of time reading about solutions to this kind of problem, so I'm just going to move on to the next one. 118, Pascal's triangle. Easy. With a fun animation. Oh, start the timer. Given an integer num rows, return the first num rows of Pascal's triangle. In Pascal's triangle, each number is the sum of the two numbers directly above it as shown. So, yeah, this number here is the sum of the two numbers that are touching it from above. Given an integer, return the first num rows. I'm having trouble understanding what that means. It didn't say what. The first num rows. Given an integer num rows, return the first num rows. Am I wrong that that sentence makes no sense? Each number is the sum of the two numbers directly above it as shown. This is a definition of Pascal's triangle. What does return the first num rows mean? So we're given an integer and we're returning a list of integers. Oh, basically return Pascal's triangle. Return all the numbers in the rows of Pascal's triangle. Why is it written like this? This is the weirdest. Okay, I should have just looked at the example input and output, but what a weird way to phrase that. All right. So just generate Pascal's triangle. It starts with a 1. It starts with one thing. I don't know why. Num rows. Let's not overwrite that. We'll call it ret, or maybe just rows. At the end we return rows. It starts at 1? Yeah, okay. So rows dot append 1. So that's always the first one. And then for n in range of num rows. But we want to start we want to skip 1 because we've already done that. So from 1 or from 2 to num rows dot append some list, and then I just want to see if I'm doing the right number. I think I'm off by at least 1. So num rows 1, 2, 3, 4. So this needs to be plus 1. Okay, now I have the right number of rows. Okay, so how do I generate this row from the last row? So row is an empty list, and then for I in range n, we're going to be appending some number to n, and the number is going to be the last row, so rows of -1, the previous row, at I plus the previous row at I minus 1. I'm just trying to, because I'm trying to, like, in my head skew this leftwards. So it's I plus 1. If these were all left aligned, then the parent of this one is going to be the one above it and the one to the right of it, or the one upright of it. So oh, and the left one and the right. Oh, actually, interesting. That's not right, because the left one should have no, should only have one number above it. So I have to actually write this down because I'm having trouble picturing it. So it looks like this. So you actually want the one before it and the one above it. That's always what you want, the one before it and the one above it. Yeah. And there's going to be no one before it on the first one and no one above it on the last one. So let's handle the cases of the nuns. So this is, let's do the one before it and the one above it. The one before it, if I minus 1 is greater than 0, else 0. And the one above it, if I is less than n, else 0. It's having an issue with this. Because I believe I'm not going far enough out. Or possibly this should be n minus 1 if it's the other way. Okay. I'm getting a lot of zeros. I must not be, maybe my parentheses are not right. Or maybe the lack of parentheses is making it mixed up. No. Oh, I minus 1 should be greater or equal to 0. You're allowed to be 0 here. Okay, submit this. There it is, 0 milliseconds, 100%. Next problem. Pascal's triangle 2. Given an integer row index, return the row indexed, 0 indexed row of Pascal's triangle. In Pascal's triangle, each number is the sum of the two numbers directly above it as shown. Start the timer. Okay, so last time we had to return the whole triangle. This time we're only returning one row of the triangle. So one obvious way to do this is to compute the whole triangle and return only the last row. And that may actually be what we do, though we don't have to remember the whole triangle. We only have to remember the last row as we go. The other way you could do this is recursively, but we can directly unroll the recursion and just remove the last row. So 4. So last row is starting at, are we allowed to start at 1? No, we've got row index can start at 0. Follow-up, could you optimize your algorithm to only use O of row index extra space? That is what we're doing. That's what we're going to start with. The extra space is just the remembering the last row. So that's a good hint that we're already doing this the best way. All right, last row for n in row or range of row index plus 1. Thing is, I want to start with 1, but they told me row index can be 0. So if row index equals 0, return empty list. Otherwise, start it at 1. For n and here's actually a very small optimization. We can instead of, well, whatever, let's just do this. All right, for n in starting at 1, or starting at 2 actually, because we've already done our 1th row here. Then at the end we're returning last row. And at the end of this loop, we're setting last row to be this row. Row is equal to empty list, and then you iterate over the values of n for I in range n plus 1. Row at I is equal to, and then we have to do this thing again where we have 2 terms. The first term is last row at I minus 1 if I minus 1 is greater or equal to 0, else 0, plus last row at I if I is less than or equal to n, else 0. Okay, the other thing is this is a list of size n, so that my indexing always works. The other way I could do this is just do row.append this thing. Um, so it's having trouble accessing the right row, which makes sense. Oh, because the row before this was smaller than this row? No. What's the reason? What is the reason? If I is less than length of last row, whatever it was. Okay, now it's having trouble with the first line. Last row at I minus 1. But how can this be out of range if we're checking if it's greater or equal to 0? The only way is if this is getting larger. Than the last row. So something is weird here where I don't have the number of cells in the rows that I think I do. So we should start at n equals 2, and then we add, and then we, yeah, so n starts at 2. I goes from 0 to 2. Then we append I minus 1 is going to be 0 minus 1, which is negative 1. So this should not execute because of the if. It should just be 0. And then on the other side, when I is 2, I minus 1 is going to be 1. Oh, which actually doesn't exist because we start with only one element. Did I just start the n at the wrong size? Yeah. Okay. Oh, and then 0 indexed. That was the cause of both my problems, I think. All right, so we don't actually need this. Submit that. Okay. 1 millisecond, I'm happy with that. I think if we submitted a few more times, we would get to 0 milliseconds. Yeah, there we go. There's some variance in the runtimes in Leetcode. So, on to the last one of the day. 120 triangle, medium. Start the timer. Given a triangle array, return the minimum path sum from top to bottom. Minimum path sum. Okay. Okay, yeah. For each step, you may move to an adjacent number of the row below. More formally, if you are index I of the current row, you may move to either index I or I plus 1 of the next row. Okay. So we've done the same problem with a binary tree before. This is basically a... actually, it's not basically a binary tree because nodes can have more than one parent. So it's not a binary tree. All right, we want the minimum path. We want the minimum path sum. So the minimum sum path, really. All right, so this is a classic dynamic programming problem. So what's the minimum, starting at some arbitrary node, what's the minimum path from there? It's the minimum of going left or going right. And then the base case is if I'm already a leaf node, my minimum path is just myself. So if so we'll define a recursion here, which says I'm at ij. No, these are integers. These are my coordinates in the triangle. So return the minimum path sum from return whichever is minimum, whichever one's smaller, from the left or the right path. So left path would be I plus 1 j. I plus 1, j plus 1. So this is one, the first coordinate is which row, the second coordinate is which cell inside the row. So it's whichever is the smallest of going down one and then either staying where I am or going down one and then going right. Okay, so and then the base case is if I is greater or equal to len of triangle, then 0 is my path sum. And then obviously the thing I'm forgetting here is you have to sum yourself into that, the value of this node into that. So this I, j. Return rec of 0, 0. So this should give the right answer, and then we can make it more efficient. So let's start by submitting that. And then, okay, it's gonna be too slow. So make it more efficient. Here's the cheap way. From functools, import cache. This is how you just turn a recursive solution into a dynamic programming solution without any effort. So that works, but we can do better than that. We can, we don't need this recursive tree, call tree at all. We can directly build the cache table and then return the 0th 0th element from the cache table with no recursion, as long as we iterate over the cells in the right order. So let's just define our cache is equal to, it's a list of lists of ints, list, int. I just realized there's a way to do this with even less space, but let's start with this. List of ints. So we'll initialize everything at 0. 0 for blank in range len of triangle of the last row of triangle. And then each of these, you have one of these for blank in range len of triangle. Then, so that's our cache. Then we're going to fill out the cache from bottom to top so that we already have the minimum paths from the bottom as we're building them up to the top. So for I in range triangle or length of triangle. Yeah, so I is the height in the triangle for j in range len of triangle -1. So j is the position inside the row. This is not iterating in the correct order. We have to go from bottom to top. So this is reversed. So yeah, and then j is fine. Either direction of within the row will work. So here we're setting the cache values. So cache of ij is equal to, so there's two cases. If I equals, and we could do this part outside the loop, which would make it slightly more efficient because then you don't have to check it on each iteration, but let's just do this the simple way first. If we're in the bottom row, so if I equals len of triangle -1, then this is just equal to triangle, the bottom row, or actually, let's just do this outside because it is actually simpler since we can assign the whole row at once. So cache of I of negative, so the last row of the cache is just equal to the last row of the triangle. Then inside the loop, we could skip the last row of the triangle because we've already set that. So len of triangle -1. The value at any given cell is equal to the minimum of the value of the cell below it, the value of the cell bottom right of it. Let's comment this out. And then at the end, you just return cache of 0, 0. I just can't avoid these off by 1 errors, can I? Oh, actually, this isn't an off by 1 error. This is because my cache is bigger than the triangle. So I'm trying to put in values that don't exist. I'm guessing that's what it is. If we look at the test case, yeah. So I was assuming that all of the rows are the size of the bottom row. But we can fix that. So for instead of iterating over the size of the last row, iterate over the size of the row that I'm talking about. Okay. Oh, I forgot to add the value of myself into here. Triangle of ij plus the minimum of the rest of the path. Okay, and I assume this is going to be faster. I can't remember what our last time was. I can see that though, right? Submissions. Okay, it's a little faster. Oops, I don't want to look at the solutions yet. How do we get to this juicy 3 millisecond runtime? There's still some stuff I'm doing that I don't need to be doing. So, I'm initializing a row, the largest row, for no reason, because then I'm replacing it. So if I instead did this for all except the last row, and then at the end here, append, instead of, or wait, that's not what I meant to do. Cache.append. Then I'm skipping one row of initialization. I'm scraping for, oh, well, there we go. I successfully scraped. 0 milliseconds beats 100%. All right, well, that's it. Thanks for watching.